Good afternoon everyone, and welcome to today's webinars, which is Reveal Hidden Reserves of Strength in Reinforced Concrete Slabs. My name's Tom Pritchard, I am Principal Engineer at LimitState, and my co-host for today is our Managing Director, Professor Matthew Gilbert. We'll be talking to you a little about how you can use automated yield line analysis to analyse reinforced concrete slabs, often showing that they have more inherent strength that you might actually assume they have using other techniques. A few of the things that we're aiming to show you are how the yield line method has been automated, removing the uncertainty that you may have missed a critical pattern, and secondly how LimitState slab can be used to rapidly analyse a reinforced concrete slab, often demonstrating that additional capacity is present when compared to other methods. And lastly, a little bit more about the features of the software. The presentation is due to last about 35 to 40 minutes, and there should be a short amount of time at the end for questions. You can post these at any time using the question panel that should be present in the webinar interface that you have on your screens. You may need to expand the menu using the out arrow to see this, but do feel free to send in any questions that you may have at the time. We'll attempt to answer as many of them as we can in the time available. Unfortunately, this isn't always possible, but we do make sure that everyone that's asked a question gets a reply after the webinar has ended. So please don't worry if we don't actually get round to yours during the webinar itself. So without further delay, I'd like to welcome our speaker today, Professor Matthew Gilbert, who'll be talking to you about automating yield line analysis, and I'll now pass you over to him.
Thanks very much, Tom, and thanks everyone for joining the webinar today. Okay, so the first slide I'm going to show just gives you an indication of the difference between conventional yield line patterns that we might identify in textbooks or by hand, a couple of them shown on the left, and the yield line patterns that we can identify for real-world complex slab configurations. So we can effectively extend that classical yield line theory to apply to completely arbitrary slab geometries. That's the key. And we can look at the yield line patterns as we are here, and we can also view them as animations, as you can see on the slide shown now, just to help the engineer or us as engineers to visualize exactly what's going on. And so what I'm going to be talking about is how we achieve that. So before I get onto the webinar proper, I'll just say a few words about LimitState, the company. It's actually been around for a little more than 10 years now. It spun out from the University of Sheffield in 2006, and really the focus is on commercializing academic research. So it's taking research methods out into the field to a wider audience, and it's providing engineers with powerful tools which are not available in existing commercial software packages. And the other thing is, as we're a commercial provider, one of our major priorities is ensuring that the software is robust, it's well validated, and it's fully supported, so that if you are a user of the software, you know, somebody at the end of a telephone line or the end of an email to provide you with guidance on how to use it, or if you run into any problems. In terms of the focus of the company, certainly the early focus and still the main focus is on tools for analysing the ultimate or collapse limit state. If we have a look at tools that are out there in the field, they tend to fall into one or two camps. The first I've identified as being traditional, so hand type calculations on the one hand. Typically, those have been automated in some way by embedding those hand calculations in a spreadsheet, a company spreadsheet could be, or in a simple software tool. And at the other extreme, we have advanced tools such as nonlinear finite elements, discrete elements, what have you. And what we've identified is that there's a large gap between those two types of tools. And the problem with the traditional tools is they tend to have quite limited range of applicability. And very often in practice as engineers, we will find that those tools don't quite serve our needs for a particular project. And traditionally, you then had to move to much more complex, advanced tools such as finite elements, etc. And what we've been focusing on is actually filling that gap or bridging that gap with a range of mainstream tools based on rigid plastic analysis techniques. And we could be talking about a geotechnical application, as you can see on screen here, or we could be looking at masonry application, in this case masonry arch bridge, or clearly of interest today, we could be looking at reinforced concrete slab analysis or design. So the benefit of these mainstream rigid plastic analysis tools that we've been focusing on is that you are free to describe the geometry in any way that you see fit, and you can also assign material parameters around the geometry again as you see fit. So it's doing things which are actually made life very difficult with the hand tools, but without the long run times and the high level of operator expertise that you typically associate with non-linear finite elements, for example. Tools that we've made available to date for construction sector professionals are LimitState Ring, LimitState Geo and LimitState Slab, basically tackling those three applications that I've just outlined. Those software applications are now widely used, so in more than 30 countries worldwide, and on the website we've got a list of some of our customers. So we've got the A's up to B here shown on screen, but there's some big names, Atkins, Arup, Balfour Beatty and so forth, who are using our software. Okay, so moving on to focus on yield line method. Some of you will be familiar with the yield line method, some of you will be probably unfamiliar with it. Basically it's a direct means of analysing a reinforced concrete slab at the point of collapse. Traditionally it's been a hand method. I think you've traced the sort of yield line sort of concept back to 1920s. The method, it typically involves the following steps. First step is that you guess a yield line pattern. You then deform the mechanism and you equate internal and external work, and then you calculate the collapse load, or if you're looking at a design problem, the required moment capacity. So it's in theory a relatively simple approach. Directly you get a measure of the collapse load or required moment capacity. When used for new design, a key benefit is that you can end up with very economical design, certainly compared with those that you would design using elastic methods. Or if you're looking at an assessment of existing structure, you can end up with more realistic estimates of the capacity of existing slabs. In other words, you can often find hidden strengths in slabs, which can obviate the need to strengthen or upgrade a given slab. So those are pros. The cons, the first one, and this has been a really big one, is if you don't choose the correct mechanism, then you'll overestimate the true capacity of the slab. And that's been a big one when the method was slowly a hand method, because there's always a worry that you've missed the critical mechanism, and then you've got this problem that there's a concern that then your design or your assessed capacity is unsafe, which no engineer is going to be comfortable with. Another con is that it only considers flexural failure, so you will need to do additional checks for things like punch and shear failure. And obviously, as an ultimate analysis tool, it also doesn't give you any indication about deflections under service loads. If we think about applications of the method, one of the sort of notable applications in the last couple of decades was carried out by Campbell Middleton and co-workers at the University of Cambridge, who applied it to the reassessment of concrete bridges. If you think about it, many of the bridges that we find on our highways, motorways, etc., date back many decades. If you're designing a bridge in the 1950s or in early 1960s, then you were probably dealing with vehicles which had a maximum gross weight of around 20 tons or 22 tons, I think was the limit in 1964. We now have 40 or 44 ton vehicles that we need to carry, so you could say almost by definition a bridge designed in 1960 cannot possibly have the capacity to carry increased loads. However, because the methods that we used at that time generally use elastic principles, it's possible to revisit those bridges using plastic principles and potentially demonstrate that there's more strength than you originally believed. And that's exactly what Campbell Middleton and co-workers did. So here on screen you can see the results for 21 bridges that they reassessed. The elastic assessment shown in red, the plastic assessment shown in green. And you can see that in many cases the target capacity of 40 tons was reached, even though the elastic capacity was very much lower than that. So how did they do the plastic analysis? What they did was take a pragmatic approach, which was to tabulate a series of potential failure mechanisms or yield line patterns. So you can see on the right there we've got 27 potential yield line patterns, and they basically cranked through each and every one of these patterns and identified which one was the governing one, and hence what the assessed capacity was. Now the only problem with that is if you're applying this to a new bridge, it's not one of the 21, and it's perhaps got a slightly different geometry to standard, then there's always a concern that there's mechanism number 28 not shown on this list, which is actually critical, and because you haven't used that mechanism in your calculations, then you will end up overestimating the true capacity. So that's where the need for a systematic automated method clearly comes into play. So bridges, one clear application, also buildings are another clear application. Probably around the same time there was research on concrete frame buildings. So there was actually a large model building built in the Cardington airship hangar some years ago, and one of the things that they investigated as part of that project was the different design techniques that you could use when designing a reinforced concrete slab. And what they found was that yield line design led to the lightest or lowest tonnage required for a given slab, but also it led to very, very simple reinforcement configuration. So we have the lowest tonnage, 14.5 tons per floor required, and almost the lowest number of bar marks, which is an indication of complexity of the reinforcement. So kind of double benefits there from using the yield line method. In terms of existing buildings, often you'll find that an existing building slab has irregular geometries, certainly likely to be less regular than a bridge deck. So we can apply the automated yield line method to such scenarios, and we could be applying it considering the end use of an existing building. For example, if we're repurposing a building, perhaps existing office building that's going to be changed to residential, perhaps with a gym with additional loadings on one of the upper stories, or, and this is a use that we've seen quite often since we launched the software, it can be used when you are moving plant around in the construction phase. So if you want to move some plant from A to B, rather than have lots of expensive props or other measures to allow that piece of plant to go across a slab, you can use the yield line method to verify that actually that's a safe thing to do. In terms of existing buildings, then deflections can always be checked just using load tests. That's something that's not such an option in the new design stage, but for existing buildings, you can often do that relatively easily. So you can do a capacity check with the automated yield line method, and you can assess service deflections using Kent Lidge, etc. Okay, so I've talked a little bit about, provided a little bit of background to the to what we've been doing in the area of automated yield line analysis and design. However, what I'm going to do now is fire up the software and really quickly run you through how you can set up and solve problems. My colleague Tom, who introduced the session, is going to go into a little bit more detail a little bit later in the session. So first thing, when you run the software, you have initial dialogue, what do you want to do, and what we can do is set up a new project which is either of arbitrary geometry, in which case we choose empty, or there are actually a couple of very simple wizards to take you through the setup of a rectangular slab with or without holes. So I'll do that briefly just to show you how it works. So basically it's a series of steps to go through. I probably should I should provide my credentials. There we are. Next thing is the geometry. So this is a simple rectangular slab, so it couldn't get much more simple than that. And so simple rectangular slab has just got width, height. We can actually put in an angle of skew if we've got a slightly it's like a parallelogram type geometry. And also I can change the supports to suit my application. So actually I'm going to change these to simple just to keep things nice and simple. And then I move on to actually what the slab's going to be made of, or already is made of if it's an existing slab. I can use an existing one definition, or I can choose to define a new one. And we're defining the slab structural properties in terms of moment capacities in the different directions, and we can have orthogonal reinforcement. We can also have skew reinforcement as well. But I'll keep it simple and move on to the next stage, which is definition of the loads. So we can define self-weight loads and also pressure loads, line loads, and point loads. For now, I'm just going to keep uniformly distributed load and move on to the next and final stage, which is providing information about the analysis. So as we'll cover later on, the method uses nodes spread across the slab, and the more nodes you have, the more accurate the solution is. But for now, I'll keep this as the standard, which is medium nodal density, and end up with our slab. And if I click the green button, then I can do an analysis very, very quickly. And what we can see is that we have effectively the same yield line pattern as I showed on my slides earlier, and the same yield line pattern as you see in textbooks. So with this very, very simple configuration, we get a very standard answer. However, the beauty of the method is clearly that we can apply it to non-standard geometries. So what I'm going to do now is go back to the new project wizard and set up an empty project. What I can do just to help me is define a grid, so I can actually draw the slab dimensions on screen. I'm going to keep this as the defaults for now, but obviously in reality you would you'd set those according to your particular needs. What I'm going to do is going to use the polygon tool to actually draw this freehand. Now, in some cases, this is feasible. In many cases, it's not, in which case you can import the geometry from a CAD file very easily as well. But for now, I'm just going to just freehand draw a simple slab geometry. So I've done that. I can now turn the grid off, and I end up with a shape that you can see there. In a moment, it is just a shape, so I need to transform it into a slab. So what I can do is I can create a new structure definition to define the properties of the slab, or I can simply use one of the inbuilt definitions. So I'm just going to actually drag and drop unit MP weightless slab definition, just for simplicity. That's the first thing. Second thing is I need to define the support conditions. What I'm going to do is just select everything, and then I'm going to pick out on the property editor the external boundaries, and what I'm going to do is probably set them to be simple for now. So I've got a slab definition defined, I've got the supports. The last thing I need to do is to assign some loading, and I can choose a point load, a line load, or a pressure load, or any combination thereof. If I apply a pressure load, I can just select everything, and again I can decide what type of pressure load I'm dealing with, but for simplicity I'm going to use a unit pressure load here. So now I have everything defined, and again I can click the green button and end up with the solution very, very quickly. So this is a nice simple mechanism, and actually it's probably a mechanism that you could have conceived by hand. So the more interesting thing to do probably is to just change these boundary conditions. So let's suppose that actually I don't have supports around the entirety of the edge of the slab. Let's suppose I have the top and the bottom edges are free. You can see that you get a different mechanism. If I lose a bit of symmetry and take off another of the supports, then we end up with something slightly different. what I could also do is actually just change the supports that are existing to be fixed supports, and you can see that that is going to change the mechanism. Sorry, I've just unclicked on that. So change those to be fixed. Let's see again how that changes the mechanism. You can see that we end up with these sort of corner fans and a slightly more complex mechanism. I haven't talked about what's in the output window. Basically, the load that I've applied is multiplied by something called the adequacy factor, and the multiplier at collapse, or the adequacy factor at collapse, is indicated in the window. So at the moment it's 4.2. I'm going to do one last thing before I move back to the slides. I'm going to take off this support here, make that completely free, and I expect that to reduce the adequacy factor. And you can see it's gone down from 4.2 to 2.6, and we now end up with a very complex failure mechanism or yield line pattern of the sort that would be very difficult to analyze by hand, and that's where this software really comes into its own. Okay, so just say a few words about how the method works before handing over to Tom. So the technology that's used is something called discontinuity layout optimization, or DLO for short. It was published in the well-known science journal, Proceedings of the Royal Society, in 2014. And we demonstrated that the problem actually boils down to a simple linear optimization problem. So the steps are as follows. We start off with our slab, support conditions, load conditions, etc. We discretize the slab with nodes. We interconnect those nodes with potential yield lines, and then we use optimization to find the critical yield line pattern. In terms of equations, what we're basically doing is minimizing energy subject to nodal compatibility constraints, and also a unit displacement constraint, taking advantage of the theorem of virtual work. It boils down to a simple linear optimization problem. In terms of the nodal compatibility constraint, if we zoom in on a node, for example the corner node identified in the diagram shown on the screen, then what we need to do is basically resolve the rotations in the x direction, and that's reflected by the top expression, and in the y direction, which is reflected in the bottom. And we show that this is actually analogous to resolving forces in a truss. So exactly the same thing that you would do if you're resolving forces in a truss. You'd resolve in the x direction and the y direction, have expressions shown. The only difference is, instead of the quantities being forces, they're yield line rotations. And if you're interested in learning more, there's actually a more accessible description in the October 2015 issue of the Structural Engineer than the explanation in the Royal Society paper. So just a few examples. Simple square slab, simple supports, you get the simple sort of X mechanism or pattern that you would expect when you have a UDL. Similarly, when you have fixed supports with a UDL, we have these corner fans, and if you have a point load, then again you can identify these fans automatically. And the big difference between the DLO method and previous methods that have been applied to this problem is these kind of fan mechanisms are identified automatically without difficulty. Also, we can apply the same method to regular slabs. So here's a slab with a hole, and for this particular problem we were able to get a better solution than any other in the literature, and it solves very quickly as well. Last one I'm going to talk about briefly is an apartment block. or slabs in an apartment block. The reason for this is that this is actually the one that's covered in the yield line design guidance document published by the Concrete Centre a little more than 10 years ago. They described how these floor slabs could be designed using the yield line method. What they did was explore a large range of patterns. You can see some of them shown, so a number of patterns on the right hand diagram, and then a folding plate fan, mechanism on the left hand one. In terms of the approach that we'd adopt in the software, the key thing is getting the geometry in, get the slab properties in, and press a button, and literally a few seconds later you get the critical yield line pattern and failure mechanism that you can see visualized on the right. In fact, this is actually quite similar to the folding plate mechanism that they identified, and actually it's only 8% more critical. In that particular document, they recommended assigning a I think it's a 15% margin of safety, so actually their design was well within that margin of safety. Okay, so now I'm going to hand over to Tom, who's just going to talk you through a few further aspects of the software that I wasn't able to cover earlier.
Thanks, Matthew. So you'll have heard from Matthew how automated yield line analysis can show that slabs may have more strength than you believe, potentially using elastic analysis methods, and you've had a quick demonstration of LimitState slab. What I'm going to do is just take you through a few more of the features of the software, starting from a relatively simple problem and building our way up. So as you'll have seen through Matthew's demonstration, start from a sort of a wizard or an empty problem. I'm just going to look at a simple rectangular slab to start with, so I'll just go through and solve it very, very quickly. What we want to do is change the boundary conditions from being fixed to being simple and then solve. So you'll have seen this earlier, and we'll get the sort of traditional envelope type failure mechanism. And we can see here that our solution or our adequacy factor is 1.22, so that's saying that the weight on the pressure load can be increased by a factor of 1.22 until this failure mechanism occurs. So things that we may wish to do to the problem. So at the moment, if I click on the slab in the center here in the property editor on the right hand side, I can see that our material is an isotropic material with an MP of 1 in each direction. If I make a new structural definition, maybe I'll change the color slightly just to make sure that we can differentiate it from the original, and maybe instead of being isotropic onto an orthotropic slab, so I can change the MP value in hogging and sagging in the first direction to be 5 rather than 1, see what the difference that makes is. So on solve, actually what I've forgotten to do is to actually apply that structural definition, so that's given me the same as previously. I'm just going to drag that over and replace it and solve again, and what we'll see now is that the envelope, the sort of central horizontal section of that, has expanded to take into consideration the fact that the MP value of the reinforcement is actually much larger in that direction. So we've very quickly switched from an isotropic slab to an orthotropic slab, and our adequacy factor has gone up by maybe sort of 200%, something like that, so from 1.22 to just over 3. What I'm going to do now is just return to it being an isotropic material, and maybe what do we want to do? Let's have a look and see what happens if we put a column in there. So I turn on the grid, and to insert a column I'm going to put it around position 2,2, just going to zoom in, draw myself a rectangle that's going to be our column, select the inside of it, delete it, and then for all of the boundaries just set those to be fixed. So I've very quickly put in a column into the middle of our problem here. To check what the influence that has on it, just solve it again, and what we can see is that we've moved from it being an envelope type failure mechanism. If I just bring this around here, you can see, I'll bring it back, we've got a combination of an envelope towards the right hand side here, and then around the column this sort of semicircular fan type arrangement as well. And this has gone from being something that we could potentially guess the critical failure mechanism by hand to one that is perhaps more complex than we might otherwise be able to consider or analyse ourselves. So you can see how complex things can get very, very quickly in there. So our adequacy factor here is increased to 2. Maybe what we want to see is what happens now if we remove the support on the right hand side. So I'm just going to take that off, make that free. So now we've got a free edge on the right hand side and a column, and I'll solve again. And now because of this free edge, we've moved away from having the fan around this column, and it's just basically a half envelope mechanism that's attracted towards that free edge. And we can see here as well that our adequacy factor is just above 1. So if we had applied partial safety factors to the problem and we got this adequacy factor, then we would be sort of on the bounds of being happy with that. That would be okay. So next thing we might want to do is potentially consider what happens if we have a column on that right hand side. So again, we can just come in and zoom in, draw ourselves a column, and select those, make the boundaries fixed as they were previously, and see what the effect of adding this extra column on the right hand side is. And now we've got a very complex sort of double fan / envelope type failure mechanism with an increase in accuracy factor, as we would assume would happen because of the extra support that's being provided. So all these things are quite sort of difficult to conceptualize or calculate by hand, just through there being ever so slight variations in geometry and support conditions. One of the other things that you may be interested in is whether or not liftoff has any effect on the problem. So if we return back to our basic rectangular slab problem, I'm just going to click finish, and again set my supports to be simple. If I solve initially, we'll go back to this traditional envelope failure mechanism with the 1.22 adequacy factor that we can see there. But if I unlock, what I can also do is select these external boundaries, and then in the property editor on the right hand side here we can see that there's an option for support liftoff. If I set that to be true and then solve again, what we'll see is a slight variation in the failure mechanism. But what's the most interesting part of it is if we look at the edges, we can see at the corners the slab is actually lifting off these supports, and the adequacy factor, because of that reduced restraint, has actually come down to be 1.13 rather than 1.22. Similarly, the last thing, because we're getting towards the end of our time, is I'm just going to quickly show you what happens for knife edge support. So I'm going to make myself a rectangular slab, but actually I'll make the size of it 5 meters by 5 meters and set the edges to be simple. So we've got a nice rectangular slab there. I can solve that, and what we'll expect to happen is what we get is the cross-type failure mechanism. But if I unlock and change the top and the bottom to be free, but then also I want to add a support along the middle, it's a simple case of drawing myself a boundary between the top and the bottom free edges, selecting that boundary if I can zoom in close enough, and then setting the support type to be a knife edge. And now when I solve, what we get is sort of a double bookend effect. And the slab can either rotate over the top of it, or if I'd make this edge free and potentially move this knife edge to the right. So if I drag it over there, what we can also see once it solves, actually it's gone too far to the right, but you can actually have it so that that edge is free and lifts up accordingly with rotation over the top of the knife edge, but without any yield line actually occurring there. So we're getting towards the end of our time for the presentation. I'll just go back to the PowerPoint. So come through some of the conclusions. So what you've seen is that the yield line method is capable of providing a powerful means of analysing the ultimate collapse limit state, and it can reveal hidden strength in existing slabs, or that potentially a new slab requires less reinforcement than suggested by elastic design methods. However, one of the things that's been suffering from previously is the lack of a general implementation, which has limited its usage in recent years. But what we found is that the yield line method has been automated, and that allows us to solve linear optimization problems that gives you fan type mechanisms or that are automatically identified, and it's all been incorporated into our software LimitState SLAB. So what next? If you're new to LimitState SLAB, then please do feel free to request a full-featured copy of the software for evaluation purposes. I'll give you our email address shortly, or you can request a bespoke over-the-web demonstration showing how we can apply the software to the different types of problems that you may face in everyday life. If you're already a SLAB user, then please feel free to send us any details of features that you would find useful to add to the software, or let us know about any interesting applications that you've used it on, so that we can let other people know about it. If you want to get in contact with us, our web address is limitstate.com/slab. You can email info@limitstate.com or telephone us during UK office hours. So that brings us to the end of the presentation part. I'll just see if you have any questions, then please do type them into the interface now, and we'll try and get round to doing them. So we've got a question. It says, how are you considering the amount of reinforcement in the slab, and is it possible to draw the real existing rebar that could not necessarily be evenly distributed? So in the slab, what you can do is you could separate it out into different zones and potentially add different slab definitions or material types with different MP values in different directions and assign them. You can't draw the rebar directly into the software, but you can assign different material properties to different areas. Actually, yeah, the time is now 1:15, so what we can do is just sum up, but we will get around to answering the rest of the questions that have come up in there. So yeah, I'd just like to thank Matthew again and thank everybody for attending the webinar today. We hope you found it informative, and as mentioned at the start, if the presentation has raised any questions that we haven't answered for you, then please do get in touch via telephone or info@limitstate.com, and we'll be more than happy to answer those questions for you. LimitState SLAB is available to download from our website, which I mentioned is limitstate.com, and for everybody who's attending today, we'll just get in touch with you over the next few days just to get some feedback, find out if you have any further questions. If you'd like to watch the webinar again, or if you think you might know somebody who would be interested to see it, then there'll be a recording available probably later on today, maybe tomorrow morning, but we will email you all with a link once it's available online. Lastly, please do look out for our other webinars which deal with LimitState SLAB and the other software products that Matthew covered right at the beginning. We'll be sending out event notifications via email in advance of these, and they're also posted on our website at limitstate.com/webinars. Finally, I'd just like to thank you all again for listening, and hope you can join us next time. Thank you.